In the early 20th century, engineers built with confidence. They used steel and concrete to reach for the sky, yet they often ignored the ground beneath their feet. They treated soil as a simple, solid platform. This was a dangerous assumption. Venice, the Campanile of St. Mark's, had stood for centuries. Then, in 1902, it suddenly collapsed. A pile of dust and rubble filled the square. The foundation had failed. The soil, once thought firm, had given way without warning. This kind of catastrophic failure was not unique. Buildings tilted, dams leaked, retaining walls bowed. No one truly understood soil. Engineers mastered visible materials. They knew the strength of a steel beam. They could calculate a concrete column's load. But soil was different. It was a complex mixture of solid particles, water, air. Its behavior changed with the seasons, rainfall, and the loads placed upon it. That hero was an Austrian engineer named Karl Terzaghi. Born in 1883, Terzaghi was a brilliant and restless man. He worked on engineering projects across Europe, hydroelectric dams, railways. Everywhere he went, he saw the same problems. He witnessed foundations settle unevenly. He witnessed dams leak unexpectedly. He witnessed tunnels face immense, uncalculated pressures. He grew frustrated with the guesswork that passed for foundation design. The accepted methods were based on tradition and rules of thumb. They were not based on scientific principles. Terzaghi believed there had to be a better way. He was driven by an intense curiosity to understand why these failures happened. His journey was not an easy one. He questioned established experts and their cherished theories. That did not make him popular. He left a successful consulting career to pursue questions in academia. At a small engineering college in Istanbul, he began his revolutionary work. He set up a simple laboratory funded mostly by his own money. Here he could finally test his ideas about how soil behaved under pressure. He ignored old textbook formulas. He listened to what the soil itself would tell him. He was determined to turn foundation engineering into a true science. He started with the most basic questions. What is soil made of? How do the individual grains of sand interact? Out of his countless experiments, Terzaghi developed a revolutionary concept: effective stress. He proposed the soil's strength does not depend on total pressure pushing down on it, but on the pressure acting between the solid grains. The water trapped in the pores pushes back. Imagine a sponge filled with water. Press it gently. The water helps support the load. Press hard and quickly. Water pressure builds and the sponge structure carries little load. Building on this, Terzaghi explained consolidation. When a load, like a new building, is placed on clay, the soil does not settle instantly. Initially, the weight is carried by pore water. Over time, the water is squeezed out, and the load transfers to the soil grains. The ground settles slowly, sometimes over many years. With his theories established, Karl Terzaghi did not remain in the laboratory. One of his most famous early successes involved a large industrial building for a steel company that was suffering from severe settlement issues. The building's foundations were sinking unevenly, causing machinery to malfunction. The structure itself was being threatened. The owners were desperate. Terzaghi was called in as a consultant. He began by taking undisturbed soil samples from beneath the sinking foundation, a novel practice he championed. Back in his lab, he tested these samples to determine their properties. He used his consolidation theory to calculate how much more the building would settle and how long it would take to stabilize. His analysis showed the worst was already over, and the remaining movement would be small and manageable. He advised the company to simply re-level the machinery and wait, saving them a fortune on unnecessary and potentially damaging repairs. His prediction proved perfectly accurate, and his reputation as a soil doctor began to grow. Terzaghi's book, Erdbaumechanik, Soil Mechanics, published in 1925, compiled his findings and officially established the field. Soon, he was in demand all over the world. He was invited to MIT in the United States, where he helped establish a leading program in soil mechanics. Today, the legacy of Karl Terzaghi is literally all around us, supporting the world we live in. Every major construction project begins with the principles he established. When engineers design a towering skyscraper, they conduct extensive geotechnical investigations. They drill deep into the ground, taking samples to be tested in a lab, just as Terzaghi did. The long bridges that span our rivers, bays rest on massive piers, whose foundations are carefully designed to resist the forces of water, the weight of traffic, all based on soil mechanics. The tunnels that carry our subways, cars, undercities, mountains, are planned using detailed models of ground behavior to prevent collapses during and after construction. The massive earthen dams, concrete dams that provide our water power, are built with a deep understanding of water pressure within the soil. The very problem Terzaghi first sought to solve, ensuring their stability against catastrophic failure. Even the roads we drive on every day rely on Terzaghi's science.